Okay, hello guys. So today we're going to go ahead and we're going to dive into Unit 4, which is linear systems. And so basically what we're going to look at today is we've already been able to, so far, create equations for different types of problems, and we've been able to solve those equations algebraically. Today what we're going to be able to do is we're going to be able to graph these linear equations, and we're going to look at what linear systems are and be able to solve those linear systems graphically. So we will be working with graphs today. So I will put Desmos in the chat once we start working through that. However, before we do that, I just want to do a brief review of linear systems. So today, what we're going to use is we're going to use a variety of Google polls. Just a reminder of how to access the Google poll. So whenever I launch the poll, the Google poll will pop up at the bottom right-hand corner. You'll select whatever answer choice you want to and then press vote. Make sure that the poll says that you have voted so that you know that you have submitted your answer. If you do not press vote, I will not get your answer. So make sure that you submit voted. And then the poll will be marked as ended when the teacher has ended the poll. So basically when that poll closes, it'll be marked as ended. Okay? Any questions about how to access the Google poll? We'll see a couple of them pop up today as we dive into Unit 4. Okay, that's fine. Okay, so like I said, today, this is our first lesson in Unit 4, and we're going to look at solving linear systems graphically. But before we do that, let's do a brief reminder or overview of how we go ahead and write linear equations. So we have looked at this before. Basically, given this information, what we want to determine is what equation represents the cost C for D days at work out gym. So I'm going to launch that first poll. You should see it pop up. And basically just select an answer choice, A, B, C, or D. Which equation would best represent or model this scenario? I'll give you about 1 minute to answer that. I see a lot of us getting it correct. About 45 more seconds. Just a reminder to answer the poll. About 20 seconds. Ten seconds. Wonderful. 5, 4, 3, 2, and 1. So let me end that poll. Oh, give me 1 second, guys. Okay, so the answer to this one was in fact B. So good job. Everybody did get that one right. So basically, it tells us that our initial fee is $15, so that's going to be our constant, and then it's a $1 fee or cost per day. So basically, we could write 1D plus 15, but you can drop that one, and you could just think that we have an imaginary one set right here. And so therefore, D would be that answer. So good job. So for every day, it is $1 per day, but there is an initial start fee of $15. So good job. What about this one? What equation would represent the cost C for days at the healthy gym? So let me launch that poll. Again, 1 minute. So what equation represents the cost C for the days at healthy gym? About 45 seconds. Thirty seconds. Great job. So most of us are getting it right so far. 15 seconds. Okay. Okay, so let me go ahead and end that poll. Wonderful job. So the answer here is D. So what equation represents the cost C for D days at Healthy Gym? Well, we know that the initial fee is $5. So our initial fee would be $5. So that eliminates B and C. But here, the cost per day is $2. And so we would have 2 times D because you would have $2 per day. And so that leaves us with answer choice D. So D would represent that equation. Okay? Any questions here? Questions, concerns? Okay. So if for some reason I wanted to identify the day, so D, when an individual will pay the same amount at the workout gym as the healthy gym, given those two equations that we just created, how could I do that? And respond to that in the chat box. If I wanted to identify the D days when an individual will pay the same amount at the workout gym as the healthy gym, how could I do that? What would I do with those two equations? How could I solve this? And I'll give you about 2 minutes to think of something and respond in the chat box. How might we identify the D day when an individual will pay the same amount at the workout gym and the healthy gym? And you're putting your response in the chat box. Please respond in the chat box. There's no right or wrong answer. If you were to go ahead and identify how much you paid per day at this gym, or if you were to go ahead and identify what day you would pay the same amount in both of these gyms, how would you do it? Okay, if you want to go ahead and keep your response anonymous, I will go ahead and upload a Google form, and you can go ahead and select on that and write your response. If for some reason you're not 100% sure and you want to keep it anonymous, that's totally fine. I'll give you about 2 more minutes to respond. How might we identify the day when an individual will pay the same amount at the workout gym as the healthy gym, given what we know right now? About 1 more minute. You're either responding in the chat box or in the Google form. You must respond, either one. I'll go ahead and upload that link again. Okay, it's interesting responses I'm getting in the Google form. What I'm identifying is that there's multiple ways to go ahead and solve for this. So great job. Okay, so if you did not go ahead and respond to the Google form or post anything in the chat box, please make sure that you are responding to these questions, as they will help me navigate what we need to go ahead and review. So I got a lot of the same responses for those of us who did respond. Basically, they were saying that we could put these two equations equal to each other and then solve for D. So yes, that is the way that we would find out what X that we could put, which would make both of those systems true at the same time. So which value, for example, D, would make both of those systems have the same amount or be equal to each other. And so D would tell us what day that they would have the same amount. So good job. Okay. Well, what we're going to learn today is there's actually an easier way to go ahead and do this. And by doing this, by representing these linear systems graphically, what we're going to be able to do, or what we're going to be able to solve, is we're going to be able to solve for a point of intersection, which basically represents our D, where both of these systems will prove true and be equal to each other. So let me go ahead and show you how we would solve this in Desmos, and then I'll go ahead and post Desmos in the chat as we move forward. Okay, so here we go. Now, the way that we can go ahead and solve this graphically is what we want to do is we want to plug in both equations. So I'm going to plug in the one that we got for the workout gym. So C is equal to D plus 15. And the one that we did for the healthy gym, which is C is equal to 2D plus 5. Let me go ahead and find that point of intersection. And what you see is that those two lines, those two linear equations, intersect at this point right here. And so what this tells me is this represents, my X values represents my D, my amount of days, and my Y axis represents my cost. So depending on the amount of days, my cost changes. Well, what this tells me is that when they intersect at 10 days, at both gyms, you'll pay $25. Because again, X represents the amount of days and Y represents the cost for that day. And so finding that point of intersection will allow us to identify the day when an individual paid the same amount at the workout gym as they pay as the healthy gym. And so that is the way that we're going to go ahead and solve what these are known as systems of equations as we move forward in this class. So, any questions about this? Questions, concerns? No? Okay. So, let me share my PowerPoint again. Okay. So let's define a system of two variable linear equations. So a system of equations are two or more equations that have common variables. So for example, our workout gym and our healthy gym equations, they both had common variables. We were comparing the amount of days to the cost, right? We use both C and D to represent those two variables, hence two variable linear equations. The solution to a system of equations, what we're solving for, that solution or that intersection point, is going to be the points or points that make all equations in the system true. So basically, if we were to plug in, we just identified D as 10. If I were to plug in 10 for both of my equations, I would get the same C. I would get that they're both going to cost $25 on day 10, which is what I'm trying to solve. What is the day that I will pay the same amount at both gyms? Okay, so what we just identified is that 10 and 25 is the only solution to this system. That's the only time in which those two lines intersect. We have a solution visibly because we have this point of intersection. So that point of intersection is going to be that solution. And so what we're going to look at is whenever we put two systems of equations together, the point of intersection will tell us the solution to that problem. And then this solution means that after 10 days, the cost of either gym is $25. So therefore, on day 10, you'll pay the same amount at the healthy gym as you do at the workout gym. Okay, any questions about this? Questions, concerns?
No, ma'am.
No? Okay, so I'm going to go ahead and plug Desmos into the chat box. And now tell me, how many solutions does the system have using the poll? So you're just responding A, B, C, or D in the poll. And let me launch it. And try to graph those and tell me if it has any solution points based on what we just learned. I'll give you about 2 minutes. Do those two graphs intersect? Mm-hmm. About 1 more minute. So basically you're graphing those two equations on Desmos and telling me how many solutions does that system have? None, 1, 2, or infinitely many? About 30 seconds and we'll go over this together. Okay, about 10 more seconds. Let me see if I can put this. Okay. Okay. So let's go ahead and see how we're supposed to graph that and what that graph tells us. Give me 1 second. Okay. So we were going to graph y is equal to 5x and y is equal to 6x. And so what you want to look for is you want to look from starting from 0, are there any intersection points? And what you notice is that those lines, no matter how far I go down this graph, never intersect. And so if there's no points of intersections, then that means that I have no solutions. Those two graphs will never have a common point that proves both of them true at the same time. Okay, so by graphing it, I can see I have no points of intersections, so therefore I have no solutions. Okay, so we're going to do one more check for understanding. Here we do have two lines that have, oh, hold on, let me reshare my thing. Okay, here we do have two lines that have a point of intersection. So tell me, what is my point of intersection? What does this point of intersection mean? Am I sharing it? It's not showing on my end. Let's see. Let me try to share that again. There we go. So where is my point of intersection? Which one would represent my point of intersection? So now we're interpreting this graph. We're not graphing it and finding the solution. We're given the graph and we're just asked to interpret what that point of intersection is. What is that solution? Oh, let me launch that poll. I'm going to A, B, C, or D. Wonderful. Keep going. About 30 seconds. Okay, so let me go ahead and share my other screen so that we can see. All of us look like we got that correct, so that one's pretty easy, but let's just go overview it. So basically, it says which point approximates the solution to the linear system graph below. Well, let us remember that the solution, whenever we graph two systems of equations, is going to be the point of intersection. Here is our point of intersection. It's not 100% easy to tell where that point of intersection is. So the best thing to do, or in my opinion, the best thing to do would be to identify where all these points are. So 0 and -1 is here. Well, that's not my point of intersection, so I wouldn't select that one. 1.25 and 0.25. So 1.25, yeah, that's approximately right there. And that's approximately right there. So maybe, let's test the other ones. 0 and 1.5. Yeah, I would say that's approximately right there. But again, that's not my point of intersection. And lastly, 1.75 and 0. I would say that's approximately right here. And again, that's not my point of intersection. My point of intersection would therefore be better approximated at B, 1.25 and 0.25. Okay? Wonderful. I guess I could have stayed there. I don't know. Let me go back so we can go ahead and go over this together. Okay, so we also have ways to classify linear systems. We can have an inconsistent linear system, a consistent and independent linear system, and a consistent and dependent linear system. So an inconsistent linear systems are going to be two lines that are parallel. Well, if two lines are parallel, we know they never intersect. And so therefore, inconsistent linear systems will have no solution. If they never intersect, then there's never a point of intersection, and so there's no solution. How about consistent and independent? Well, linear systems that are consistent and independent have lines that intersect at one point, so they have one point of intersection. And so if they have one point of intersection, then that means they have exactly one and only one solution. And so this would be that point of intersection right here. Okay. So now we also have consistent and dependent. These are lines that coincide with each other. So we can't really see it here, but basically what you can think of, and I can go ahead and draw it, is if we had two lines, hold on, if we had two lines, I'm going to try my best to draw this. That were kind of on top of each other. If I had two lines that were exactly the same on top of each other, basically, well, then those two lines would coincide with each other. They would continue to intersect as we move through the lines. And so what that tells me is that those systems of equations have infinitely many solutions. This point can be a solution, point of intersection. This point can be a point of intersection, this point, and so it's infinite many solutions. So inconsistent means no, absolutely no solutions. Consistent and independent means it has a solution, but it only has one. So basically those two lines move independently of each other, but they do intersect at one point. And then consistent and dependent, those two lines are basically dependent on each other. So they're moving at the exact same rates. So they are exactly the same. And so because of that, those lines will continue to coincide and have infinitely many solutions. Okay, 1 second. So now let's actually look at some systems or equations or some linear expressions that are dependent of each other. Well, we know when things are dependent of each other, those lines are going to coincide infinitely many times. So they're going to have infinitely many solutions. So what we want to identify is, are these two equations dependent? Are they dependent? Do they have infinitely many solutions? Well, there's two ways that we can go ahead and figure this out. We can use algebra. And the way we use algebra is here we're given our x's, so we can plug these x's into this expression and see what we get out as our y and plug that in. And we can put our x's in here and see what we get out as our y. Or what we could go ahead and do is we can graph these two and see, are they in fact dependent on each other? Will those two lines continue to coincide with each other, giving them infinite many solutions? Well, the first thing I'm going to do is I'm going to go ahead and solve it algebraically. Just for us to see, there's two options or there's two ways of solving. So here we have y is equal to x minus 4. So let's test the first x, negative 2. Negative 2 minus 4. Well, negative 2 minus 4 is negative 6. Now let's plug in 0. Y is equal to 0 minus 4. Well, that's equal to negative 4. Y is equal to 2 minus 4. Well, that is equal to negative 2. And so if I want these two solutions to be dependent of each other, have infinite many solutions, what I'm going to want is for all of these y's to match the y's that I were given in the other expression, because that means that those two lines are basically the same. They give the same output for every input you have. For every x you insert, you get the same y. So let's go ahead and test it. The first thing that I would go ahead and do is I would rearrange it to where I have my y isolated on one side of the solution. But if for some reason you don't want to go ahead and do that, you can also solve for y just by simply plugging in those x's into that equation and then rearranging it. So 2, negative 2, minus 2y equals 8. Well, 2 times negative 2 is negative 4, minus 2y equals 8. Now I'm going to go ahead and isolate my y. So plus 4, negative 2y equals 12. Divide by negative 2 on both sides. Y is equal to negative 6. So y is equal to negative 6. Well, look, those two match. Let's see if these continue to match for all of these different x values. So 2, 0 minus 2y equals 8. 0 minus 2y equals 8. Well, I can do away with the 0 because it's just a 0. So negative 2y equals 8. Divide by negative 2 on both sides. What does that tell me? Y is equal to negative 4. Well, look, those two match as well. So I already have two similar solutions, two similar points of intersection, which is a good thing. Let's see what the next one is. So now I'm going to plug in 2. Hopefully I can fit it here. And 4, and 2y. And y is equal to negative 2. And so those also match. And so what this is basically telling me is that I have multiple points of intersection. If I were to graph these two lines, they would intersect at where x is negative 2. They would intersect where x is 0. And they would intersect where x is 2. And so that means that I already have more than one solution, which means that I'm moving into the area of being dependent. Being independent tells me I have one solution, but I already have more than one solution. So I'm moving into the territory of being dependent. So now what I want to go ahead and show you is if I were to graph these two expressions, what would I get out? Would I get out a graph that looks like a consistent and dependent set of solutions? Let's go ahead and look at that. So let me plug these in. The first one is y is equal to x minus 4. And the next one is 2x minus 2y equals 8. Let's see where those graphs ended up. Look, you can't even see them. You really have to click on these different colors to be able to see them pop through. And so that means that those two graphs are basically the same. And so that would mean they have infinitely many solutions. They would continue to intersect, continue to have points of intersection at every single point. And so because of that, they are consistent and dependent. Okay. So that being said, let's go ahead and just look at this one more time. That being said, once again, inconsistent solutions have absolutely no solutions. Consistent and independent have exactly one solution, so they have one point of intersection. Consistent and dependent means their lines coincide indefinitely, and so they have infinite many solutions, okay? That being said, let's do a quick check for understanding. Which equation can be paired with y equals 3x minus 2 to create a consistent and independent means one solution, system? So let me put Desmos in the chat once again. Basically, you're going to graph that solution, graph the answer choices, and see which ones are consistent and independent. So we're practicing graphing these. I'll give you about 2 minutes. So you're graphing and then answering the poll. And then here you need to look at the answer choices. Is the answer choice 1 and 2, 2 and 3, 1, 2, and 5, or all of the solutions? In relation to this equation, which equation or which equations would create a consistent and independent solution? Meaning lines intersect at one point in exactly one solution. About a minute and 30 seconds. About 30 seconds. Most of us looking like we're getting it correct, so good job. Make sure to answer the poll after you've graphed all of those solutions, or all of those different equations. Okay, so let's go ahead and review these. Oh, let me make sure I ended that poll. Okay. So, how would we solve this problem? We would graph each of those in Desmos or on our calculator. And so this is the equation that we're given. We start with y equals 3x minus 2. And so what we're looking for is which of these other expressions, these different linear equations, will give us exactly one intersection point. Exactly one, not more than one, exactly one. So let's test the first one. Well, there is one intersection point and exactly one intersection point. Right? We can see those two intersecting. Next one. Same thing. There is one point of intersection right there. So that one would also be a solution. This one, well, you can't even see it. Look at it. It's right on top of each other. And so that means there would be infinitely many solutions. And so we wouldn't select that one because we're looking for consistent and independent, not consistent and dependent. Next one. Same thing. Look, those two are graphed on top of each other. That's why we can't even see them. And so that would be consistent and independent. And then the last one. Again, one point of intersection. If we look at it in the grand scheme of things, they only intersect at one point. Okay, so that would leave us with 1, 2, and 5. 1, 2, and 5 are all solutions that only have one intersection point. So therefore, our answer was D, or C, sorry, C. Good job. Okay, so almost done. Now we're going to look back at systems of inequalities. So remember, systems of inequalities are basically linear equations, but instead of using an equal sign, we use different inequalities like less than or equal to, greater than or equal to, greater than or less than. And so what we also notice is we also get solutions to these types of problems. So for example, here I have y is greater than 3x plus 4 and y is less than 3x minus 2. Well, as I graph those two, and I know how to graph those, we've gone over that. I know how to graph those. What I notice is they never intersect with each other. Those two do not intersect with each other. Neither of those equations ever intersect. And so that means they have no solutions. However, if I put y is less than 3x plus 4 and y is greater than 3x minus 2, what I'll notice is when I'm graphing them, they'll have an intersection, and our intersection will be this strip right here. And so I can go ahead and show us that on Desmos, because it's a little easier to see on Desmos because it does show the overlapping. So give me 1 second. So I have y, and I need to get those, hold on, greater than or equal to. Okay. It's telling me y is less than or equal to 3x plus 4. And y is greater than 3x minus 2. Okay, and so I have both of my equations. And so basically, when I'm looking for a point of intersection here, it's going to be, the points of intersections are going to be this part because they share this part. However, if I were to have y is greater than 3x plus 4 and y is greater than 3x minus 2, what you'll see is now those two systems overlap with each other. And so that means they have infinitely many solutions. Specifically, all their solutions exist on this side of the line, on the right side of the line. So all of these points, any point that exists in this area, this shaded area, would be a solution to those two sets. It would make both of those sets true or equal to each other. So what can we do with this information? Well, we'll go ahead and I'll show you. So basically what you're looking for whenever you're looking for solutions of a system of inequalities is you're looking for that commonality. Where do they overlap? When I graph both of those two equations together, where is the overlap? And that overlap is going to represent all the possible solutions that you may have for that inequality. So, for example, here I have two inequalities plotted here. I have y is less than 3x plus 4 and y is less than 3x minus 2. That gives me this solution. Okay? Well, what this is telling me is that my solution will exist over here, past this equation, because here there's no commonality. But over here, as that graph continues to move through, the commonality is going to be right here. And I can show you that. Or that's actually the one we just graphed. Great thing. Okay, so that's the one we just graphed. So we did see that there was commonality. There was an infinite many of solution sets. So that being said, what we can do with this is we can determine whether each point is a solution to the system. So I want to determine, is 0 and negative 2 a solution to the system? Well, what I'm going to do is I'm going to graph it. 0 and negative 2. Well, that's right here. What we notice is that those two lines do not overlap right there. And so because of that, that would not be a solution to this system. What I really want is for my solutions to my system to exist in this green area. Because if it exists in any part of this green area, then that's going to be a solution to my system. So now let's try 5 and 0. 5 and 0 is approximately right here. Well, what you'll notice is it is in that green area. And so therefore, it would in fact be a system. And so a solution for my system. I want to go ahead and show you. I'm going to graph those 2 points. I'm trying to see if I can get it as best as possible. Okay, there we go. Perfect. Okay. So let me show you exactly what this looks like. Okay, so this is the same graph we had, right? And this is what it looked like in that answer question that we just had. Now, what I want to identify is, does those points give me a solution to my system? And what I'll notice is that there's an overlap in this green one and this purple one right here. Those two linear equations or linear inequalities would have similarity in this shaded region. And so that means that all the points or all the solutions would exist within the bounds of the shaded region. So the first one was 0 and -2. And what I see is that, yes, that's on the line, but it's not in this shaded region. This shaded region would represent all those different solutions. How about 5 and 0? What we notice is it is in that shaded region. It is where that overlap occurs. And so because of that, that would be a solution to my system. If I wanted to, I could test other points, like, for example, 5 and 3. Well, look, that's also a solution to my system because it exists within that shaded area. However, for example, 2 and 0, not 2 and 0, 0 and 2. What you see is that only exists or proves true in this green part. So it only proves true for this equation right here. Y is less than or equal to 3x plus 4. But it does not prove true for this purple graph as well. And so, yes, it might be a solution for one of the inequalities, but what we're looking for is a solution for the systems of inequalities, so both of them. And so we want a point to exist in both of those bounds, both of those shaded areas overlapping each other. Okay, questions? Okay, so let's go ahead and do a quick check for understanding, and then we're done. Okay, so given that, what is the solution to the system shown? Again, you want to put these two inequalities in Desmos and then answer the question. So based on the graph you're going to get, you're going to be able to interpret the solutions. So try those out. And I'll go ahead and put those equations into the graph in case for some reason you can't do the greater than or equal to symbol or the less than or equal to symbol. So I'm graphing those two inequalities, and I'm looking for the intersection. I'll give us about 1 more minute. Okay, so let's go ahead and go over that together. Let me see. Okay, so what we want to do is we want to graph both of those inequalities like you see me doing here, and we want to find where those overlaps are. Well, for this specific equation, there is no shaded overlap, but there is an overlap, and that overlap is going to be in this line. At these different points, that is where, or at all of these points that exist on these lines that they share this line, right? We can kind of see that they share that line right there. So all those points on that line would be the solutions to these inequalities, all those different points. And so when we're selecting an answer choice, our answer choice, we want to select the points on the line. Yes, good job. So points on the line. Great job. Okay. So what we've gone over today, we went over systems of equations. We looked at whenever we have a system of linear equations that use the equal sign, what those solutions look like. And so we have different types of systems of equations. Solutions to a system of equations are the points that make all of the equations or inequalities of a system true. So what points will make these two linear inequalities equal to each other and make both of them true at the same time? We have consistent and independent, which are going to be, they are consistent, so they do have a point of intersection, but it happens at one and exactly one intersection point. We have consistent and dependent, meaning they're basically the same line, so they're going to have infinitely many solutions. They're going to coincide with each other as they continue to move through the graph, so they're going to have infinitely many solutions. And then lastly, we have inconsistent, meaning there are absolutely no solution points because those two lines will be parallel to each other, so they'll never intersect. So what about systems of inequalities? Well, we can also find solutions for systems of inequalities, but it really just depends on the relationship between those systems of inequalities. If we have two graphs that look like this, well, obviously they never intersect with each other, so we have no solutions, absolutely no solutions. We could, however, have instances in which those two equations overlap only in the middle. And so that would be a line or a strip of solutions. Or we could have my two inequalities intersect, but probably intersect in a larger shaded region. Or what we could have is systems of linear inequalities that intersect at specific planes. And so we'll get into that more on Monday. But basically, it's just having two inequalities graphed. And whenever we identify where that area that they share is shaded, that shaded similar area, does it occur in a specific plane? And so we'll look at that on Monday. Okay, so common types of questions, classifying a system. We can determine if a system has a solution. If so, it is consistent. So if it even has a solution, then it's consistent. But now I want to go from there and determine, is it independent or is it dependent? So that we'll make that determination depending on how many types of solutions we have. We'd also be able to determine whether a point is a solution to the system. So basically, we could do it two ways. We can substitute the coordinates into each equation or inequality to the system and see if it makes it true. Or we could graph that point as well as each of our linear equations and see if that point falls into an area of intersection. We can solve a linear system of equations. We basically graph each equation and find the points of intersection if there are any. And then we can solve a linear systems of inequality. Basically, we graph each boundary line and then test a point to determine shading. So basically, we're graphing those linear inequalities, which we've done before. But now how do we prove how do we solve those linear systems of inequalities? Well, we want to find where the shaded areas intersect. Where is their commonality? And that commonality section is going to be our solutions. Okay? Here are different words to know. We looked at inconsistent systems, systems of equations, dependent systems, solutions to a system of equations, independent systems, and consistent systems. So we looked at all these different terms today. Any questions about any of these terms that we've looked at? No? Okay. No. Okay. And so as you close out today, there is an exit ticket to respond to. It's going to be in the classwork tab under Friday. Basically, you're going to see if you can respond to this question. If you can respond to this question, then you've gotten everything you need out of this lesson. If not, then I'll go ahead and address those issues on Monday when we come back. But basically, take some time, see if you can respond to this question. If you cannot, that's totally okay. That means we'll go ahead and review some things. And if you can, that means you're ahead of the game and you're ready to move on to the next part of this unit, okay? So you can respond to this now. You can respond to this until 11:59 p.m. tonight. Whatever your preference is, just make sure you respond to it so I can see where you are as far as this lesson goes, okay? Questions? No? Okay. I can also go ahead and quickly just put it in the chat box if you guys want to respond to it right now. So let me get it. If for some reason you do want to do it right now, that's totally fine. And then I'll use these responses to kind of gauge where we're at. Okay, so I have put it in the chat box. If there's no other questions, you guys may log off, and I will see you guys on Monday. Have a great weekend. Bye, guys.
Bye, Miss.
Bye.